today's notes are going to be about Lewis dot diagrams and covalent bonds. Now, Lewis dot diagrams, probably the easiest thing that we've done all year. So what a Lewis dot diagram is, if we talked about on the do now how the valence electrons are the outermost electrons, and when you go to figure them out, in case you forgot, it's the ones place of the group number, or you can actually write out the electron configuration and look at the Bohr model and count up the outer circle. I didn't want to just tell you it was the ones place. I mean, it's not like I didn't explain it, right? But it's basically, if you look at the Bohr model, it's the outermost electrons. But if we start with carbon, carbon's Bohr model looks like this. Okay, so what I'm doing there, first of all, I'm drawing the symbol. I am identifying the number of valence electrons, however it is that you like to do that. Number of valence electrons, and VE is valence electron. And then I am, you know how Hund's rule, we filled one orbital at a time? We're kind of using that same idea. Place dots, which stand for the electrons, around the symbol, one side at a time. So notice I don't have 4 all clumped on one side. Place dots around the symbol, one side at a time. You can tell this is going to be very difficult, isn't it? Super hard.
Rocket science.
Yes, indeed. So let me do a couple more examples for you. Please do remember that helium, this may trip you up later, helium only has 2 valence electrons. So even though it's in group 18, it only has 2 valence electrons because it only has 2 electrons. So careful there. But so if I do hydrogen, right? Hydrogen's Bohr model looks like that. Very, very confusing, I know. And that's it. And so if I do another one, let's say I do fluorine. Fluorine has 7 valence electrons. So if I go 1, 2, 3, 4, 5, 6, 7. I'm just going to scoop hydrogens down. Just go with me. Scoop. There you go. Now, we talked about the reason why things bond. I mean, it's due to electronegativity differences and how strongly atoms can pull on electrons. But it's very stable to have the electron configuration of a noble gas because they have their valence shell full. So they don't need to either lose any or gain any. They're very stable. So what happens here, you can see in yellow, this is not permanent yet, but if hydrogen were to have 2 electrons, it would have the same electron configuration of helium. And so it would be full there. And if fluorine would have 1 more electron, then it would have the electron configuration of neon, and it would have a full valence shell. So what ends up happening, you can't just get electrons out of nowhere, right? They end up sharing. And so what occurs is these actually, because fluorine is electronegative, right? Fluorine is the most electronegative element. It will actually pull on this electron of hydrogen, and it's not ionic, is it? Right? So this is covalent because they're both nonmetals. But what will happen is these will form a bond, and basically it looks something like this. Here's your hydrogen, and now here's your fluorine when we draw the model. And notice how these 2 electrons are shared. So that's a covalent bond. They're shared. And fluorine is more electronegative. I think its electronegativity is 4, and this one's 2.1. So you have a difference of 1.9. Yeah. So it's definitely polar. Actually, that's strong enough to be ionic. But if you have two nonmetals, then it's still covalent. But big difference in your electronegativity here. But anyway, they're shared. And what ends up occurring, if I draw this one more time, is that these two shared electrons, they look like that. They're notated as being a line, and this line is the bond. So that's a single covalent bond. And so one single covalent bond means there are two shared electrons. This is that. They're the same. So, single covalent bond. And that means you have two shared electrons. So when we know how to do the Lewis dot structures, right? But when you take it a step further and things bond, some of the dots, some of the electrons end up becoming the bonds. So I didn't do any kind of magic. I didn't take any electrons away. If you look where I started, I had 1, 2, 3, 4, 5, 6, 7, 8 electrons. And I still have 1, 2, 3, 4, 5, 6, 7, 8. None of the electrons were like gained from the universe, but I'm just showing how they're going to be shared. How do you feel about that? It's okay? I'm going to show you what a double bond looks like. Guess how many lines it has? So smart. So what if something, again, I'm dealing covalent here, so I'm looking at nonmetals. If I had something like sulfur and oxygen bond, okay? So I've got sulfur, and then I have oxygen. Do you see how they both have 6 valence electrons? How many more electrons do each need to have a full octet? Right. This is the key. Every time a bond is made, okay, you basically bring your electron. Brooklyn, how are you for a second? I have an arm. Let's pretend like I'm missing an arm. And Brooklyn, be missing an arm. Brooklyn, be missing an arm. Not that one. Thank you. So we both need an arm, right? So we can hold hands here. Now I have 2 arms and she has 2 arms, but we both brought one. You see? Yeah. So every time you make a bond, it's like getting an extra electron, but I didn't take her electron, we just shared it, yeah? Didn't take her arm. So what ends up happening here is I have these electrons here will be involved in bonding, and it will look like this. Now, today, don't worry about how I'm figuring out where to draw the stuff and how to move it. I'm going to give you rules and everything tomorrow, but these will basically, those 4, let me draw it this way first. Those 4 electrons, what color am I here? So here's sulfur's 2 electrons, here's oxygen's 2 electrons, and then the oxygen still keeps the other 4, and so does the sulfur. And now that is notated like this. So there are 4 electrons there, and then these 2 stay there. And I'm drawing the electrons catty-corner like that on purpose. Don't worry about why. I'm getting to that later. So that means there are 4 shared electrons. 4 shared electrons, which is called a double bond. Happy times? Guess how many lines are in a triple bond? You're so smart. Okay. So, you know how I told you yesterday that sometimes elements can actually bond to themselves? So nitrogen does that. I'll make this nitrogen blue and this nitrogen red. And so nitrogen has 5 valence electrons. 1, 2, 3, 4, 5. And so how many bonds will it need to form to have a full octet? That's 5. How many more does it need? 3. So we make 3 bonds. However many you need, how many bonds you're going to make, okay? So, and you can see that, I'll show you. So what ends up happening, here's your nitrogen, here's the other nitrogen. And so 1, 2, 3 electrons will be involved in this little party. and then they will still maintain. These are called lone pairs. They're not bonding pairs. These are bonding pairs. Because that's really 6 dots there. Do you need me to draw 6 dots? You okay? Now look. This nitrogen right here has 2, 4, 6, 8. This nitrogen has 2, 4, 6, 8. And then total 2, 4, 6, 8, 10. I came into here with 10. So no electrons were lost or gained, but they've just been rearranged so they can be shared, and then they have a full valence shell. This is a triple bond. It involves 6 shared electrons. This is the hardest thing we've done all year, ain't it?
Yes.
Really?
No,
Not really. Okay, good. So what I want you guys to do now is you're going to do the front page of the practice I gave you. It says Lewis practice, and you're just going to be drawing the Lewis structures.